Hello, am I audible? Hi, am I audible? Okay, so good afternoon. So I am Subrata Samanta and I am your teaching assistant for the thermal physics course taken by Professor Demala Banerjee at this semester at NPTEL. So today, okay, so let's first share the screen. Okay, so my screen is visible now, right? Hello, my screen is visible. Okay, thank you. Okay, so today I'm going to discuss the week 4 content regarding the Brownian motions of particles stated that, and then we solve the week 4 assignment problems. Okay, so before we start, in the previous sessions we discussed something about the diffusion process very briefly. So today I am start from the diffusion process, and then slowly we go into the Brownian motions, and then we discuss that how they are related. Okay, so diffusion process, the Brownian motions of the particles related to the diffusions. Okay, so the diffusion is very important things you have to understand at these levels, because uh, this diffusion process related to the Brownian motions, and Brownian motions is very interesting phenomena. Okay, so you have to understand at these levels. Okay, so let's start with that, the Brownian motions. Okay, so first we discuss about diffusion process. Diffusion process, and then we go into the Brownian motions, Einstein theory. So Brownian motion, Einstein's theory, and then we go into the Langevin's formalism. Langevin formalism, right? So in the meantime, we discuss the assignment problems and related your doubts. So we discuss. Okay, so okay, so before we start, is there any problem in the week content or in the assignments? Okay, so we start systematically one by one. So then so okay, so what is Brownian motions? Okay, so Brownian motions, so let's first briefly discuss about the main point of the Brownian motions. Then we go back to the diffusion equations, and then how to connect with the diffusion equations to the Brownian motions. Okay, so the main point is the Brownian motion is that Brownian motion. Okay, so can you tell me the in short that what is the Brownian motions, and what kind of motions is called the Brownian motions? Yes, so it's correct, but the point is that okay, so we have to remember that the main points of these Brownian motions, that the motions is independent of any mechanical vibrations of the container. That means we are not putting any external force on that. Okay, so this purely is the internal motions, and we are not putting any external force. That means the motions is independent. So motion is independent of any mechanical vibrations of the container. Okay, so mechanical vibrations means that we are putting external force to the container, and then the container vibrates, and due to this container vibrations the molecule getting a vibrates. But this kind of motions is not a Brownian motions. Okay, so motions is independent of mechanical vibration of the container. Do we that the suppose in the smaller in the size, okay, smaller in the size of particle, smaller in size, okay, so greater the motions. So size means the particle size, okay, so smaller in particle size, so greater in the motions, greater is the motions, okay. And third is that so lower the viscosity of the medium, lower the viscosity of the medium, this leads to the greater the motions, okay, so greater the motions. And fourth is that the higher the temperatures, so higher the temperature leads to the greater the motion. Okay, so these 4 points you have to remember. And okay, so suppose you consider a vibrations in a lattice, okay, so this kind of vibrations is not external, okay, so internal vibrations of the lattice. This kind of vibrations you can consider as a Brownian motions, lattice vibrations. No, lattice vibrations is not a Brownian versions, because they are rapidly vibrating. Okay, so that's why we are not considering the lattice vibrations as a Brownian versions. Okay, so you have to remember that this kind of vibrations, the lattice vibrations, is because they are vibrate too rapidly. Okay, so that's why that on the time average we are not getting the experimental values, right? So we'll discuss this thing that lattice vibrations is not a Brownian versions. Okay, so because we have calculated the mean square displacement of the Brownian particle in terms of the transport property of the host fluid, right? So experimentally verified by Perrin in 1909, right? So when we calculate this over a long time, and we not get correct results for lattice case, I think. So that's why the lattice vibrations is not say Brownian motions. Okay, so we'll discuss that. Okay, so and this kind of all the issues are Einstein was the first to formulate a correct pictures of the entire problems. Okay, so when the particle size smaller, the greater in the motion, and the lower the viscosity, greater in the motions, higher the temperature, greater in the motions. So all these problems are Einstein was first to formulate a correct picture for this entire problem. Okay. So okay, so first we discuss the briefly about the diffusion process, and then I will like to discuss how the irregular movement, okay, so irregular movement of the particle suspended in a water related to the diffusion. Okay, so I would like to address these questions that how the irregular movement of the particles suspended in a liquid, suspended in a liquid related to the diffusion, related to the diffusion. Okay, so before we go into that, we first discuss about the diffusion process. Okay, so okay, so diffusion process, and let's say, okay, so start. So let's say thermal diffusion equations. So start with the thermal diffusion equations. Thermal diffusion equations. What is it? Okay, so in the previous chapter we calculate the heat flux, and then we how to relate is the temperature gradient, and the coefficient is called the thermal conductivity, right? So in this chapter we will look this problem, okay, and using that the K question is that how the heat, okay. So in the previous thing, when we calculate the thermal conductivity, we calculate the heat flux J vector, and this minus kappa delta T, right? It's a gradient of the temperature related to the heat flux, and this is actually the thermal conductivity. But here I would like to ask the questions that how heat appears to diffuse from one place to another place. How heat appears to diffuse from one place to another. So one place to other, okay, right? The question is clear. How heat appears to diffuse from one place to another, okay. And that's these questions actually tells the thermal diffusion equations describe this kind of phenomena, the how heat appears diffuse at one place to another, okay. So this actually the thermal diffusion equations tells this problem, okay. So let's start with again the from the heat flux, okay. So once you know that the heat flux is J vector is minus kappa grad T, and this kappa is the thermal conductivity, okay. And similarly so this is come in the, okay, so let's say kappa is the thermal conductivity, okay. Yeah, so this is in 3 dimensions, okay. So in 3D, okay. So let's go back to the previous case where we discussed this thing. Just recall our previous notes, okay. Yes, so here, so in 3D that heat flux is J is related to the kappa, and grad T is the temperature gradient. This minus sign, the heat flow from, okay, so heat flow from hotter body to colder body, okay. So heat flow from hotter body T1, and let's say it's the colder body, okay. So T1 is greater than T2, but the heat flux in the opposite way, right? Against the temperature gradient, okay. So you say that the temperature gradient is T2, T1 and T2. The temperature gradient, because T1 is greater, so temperature gradient in this direction, okay. Let's say we call this blue. So the temperature gradient in this direction, and heat flow from hotter body to colder body, okay. So the heat flow in this direction, so this is the flux J, so it's the opposite direction, that's why it gives a minus sign, okay. It's clear now, right? Why there is a minus sign. So similarly when we discuss the diffusion equations, okay, so this is this consider the temperatures. Now we consider the particles, okay. So similarly the particle flux in 3 dimension, okay. So similarly particle flux in 3 dimension is called phi. So this is heat flux. Now we consider the particle flux, and this particle flux, similar equation, minus d gradient of n, right? So heat flux driven by temperature, particle flux driven by number of particles n, right? So this d is the diffusion constant. So this d is the diffusion constant, right? So so look at the similarity, okay. So mathematical similarity of these two equations, okay. So now recall our electrostatic case, okay. So let's say the flow of electrical current is given, the flow of electrical current is given by the charge current density, right? So current electrical current is given by the current density. So in this case we write that the Je, the current density, is like a flux, okay, heat flux is similarly like a current density. This is actually sigma into E, where sigma is the electrical conductivity, okay, and E is the electric field. So E, where the E is the electric field and sigma is the electrical conductivity. Okay, electrical conductivity. So if we write this Je into that, what is the E? E actually the minus grad of phi, right? Phi is the potential, scalar potential. So if we write, then we get that minus sigma times grad phi. Okay, so similar kind of things. Okay, so J equals to minus k grad t, kappa grad t, phi equals to minus d grad a, and J equals to minus sigma grad phi. So we can relate that all these equations are the mathematical similarity, right? So it's like a diffusion equations. So this is also like a diffusion equations. This is also like a diffusion equations. Okay. So we go one by one. Okay. So let's first goes to the first case. Okay, when the temperature. So this question. So we first address this question, that how heat appears diffuse from one place to another. That means how the temperature evolves. Okay. So then. Okay, so this point is clear, right? So this mathematical similarity between these three, okay, between these three different things. Yeah, so this same kind of structure where the phi is a potential and J is the current density, and in this case the particle flux, heat flux, same kind of things. So now we going to calculate, let's say, on first thing, okay, first case, and we address this problem, okay, how this temperature evolves, okay. So then let's say consider a closed surface S. Okay. Okay. So one thing I have to know that so when a line, right? When a line in a plane and we have closed this line, right? You got an area, right? Because you have to bound the region. So closed line means area. When we closed the area in the 3D, then we get a volume. So closed surface area means a volume. Okay. So when we this consider a closed surface around your system, okay, and it's a volume V. So okay, so closed surface, right, explicitly the closed surface is encloses a volume V. Okay, so closed surface means that the volume. So we consider the volume B, and let's say the heat flux from this surface is perpendicular to this. Okay, so it's like a Gauss theorem. Okay, so this is a J vector heat flux. Okay, so we are not considering any external source. Okay, so we are not considering any external source. Not consider any external source. That means there is a no heat source. Okay, so they pump the heats. Okay, so there is a no external heat source. So that means your energy is conserved. So energy is conserved because we are not putting any external heat source. So energy is conserved. That means you cannot destroy heat. Okay, so you cannot destroy, okay, heat. Okay, so only treat the thermal case here. Okay, so energy is conserved, you cannot destroy the heat. So now we calculate the total heat flow out heat flow out of this closed surface. Okay, so you calculate the total heat flow out of a closed surface. Okay, so total now we calculate the total heat flow out of a closed surface. Can you tell me what is the answer? Total heat flow out of this closed surface. We know that the heat flux is J. So heat flux is J. Flux means that the out. Okay, so how much heat going through this surface. Okay, and we enclose this surface. So that means we integrate this. This S about the surface. J. This is the flux dot ds vector. Okay, so that is the total heat flow out of this closed surface. Okay, so this is equals to, yeah, so this is equals to what? So what is the dimension of this quantity? This is the heat flux and this is ds. So if you calculate the dimensions, okay, so the dimension of this quantity, dimension, actually the dimension of power. Okay, so that means joule by second. Okay, it's the work per time. Okay, it's the power. So that means the work is joule and is the second. So that means you so therefore this is equals to the rate of material inside this surface losing energy, right? So you get the heat is flux, so this is a heat flux and is radiated. So the material inside this volume losing energy, and that's Pariman energy is going outward. Okay, and because energy is conserved. Okay, so whatever this the energy passing through this surface, that means that the inside the materials must be lose this kind of energy. Okay, that much energy the inside the material loses and outside, that's why they flow. Okay, so this is actually the minus the del T of V C T dV. What is this quantity? Okay, so the del T, this means the rate of change of the total thermal energy inside the volume. Okay, so inside the materials that changes the energy, and that energy going through the outwards. Okay, so the flux. Okay, so this point is clear or not? So I'm going to the what is this quantity. Okay, so this equation is clear or not? Yeah, so now this actually thermal energy. So what is the thermal energy? So the rate of change of the thermal energy, because the material that has the energy. So this is called the thermal energy. Right. So where C, yeah, so where C is the heat capacity per unit volume. So in the previous class I tell that the what is the heat capacity per unit volume. So the heat capacity per unit volume, this is C, and T is the temperature. And when we this unit volume it multiplied with the small volume dV, okay, we get a heat capacity, and the rate of change of the heat capacity is actually, okay, so heat capacity, what is the unit of the heat capacity? What is the dimensions? So heat, this is the dimensions, actually the unit is joule meter to the power minus 3 Kelvin inverse, right? So when we multiply with volume dq dv, so this means, so let's say when we multiply dv, so that means joule Kelvin inverse. So we need T, right? We get a joule per second. Yes, this is the dimensions of power. So these things the dimensions of power. Okay, that means the joule per second. So delta T is a second. So we need this from this quantity joule, right? So by dimensional analysis, we can tell that the thermal energy in this form, C thermal energy in this form. Okay, so C T and dV. So you can ask that if we add a thermal energy, let's say constant things. Okay, so we do not know exact thermal energy, but the dependence of the thermal energy, temperature, and this. So you can shift the thermal energy by a constant, but this does not mean anything because we are derivatives with respect to T. Okay. So if we add any constant energy to the thermal energy, so this does not change. Okay. So now from these equations, what we can conclude this thing. Okay, so this point is clear, right? Okay, so now we use that. Okay, so here we tell that the closed surface is actual the encloses the volume V. That means the surface integrals is somehow replace the volume integral, right? Because if you want a closed surface integral, it's somehow related to the volume, right? So that means that that's the divergence theory tells. So divergence theory tells that divergence theorem. So divergence theorem implies that so that you have a closed surface is J dot ds. So it looks like a volume integral because the closed surface is actually a volume, gives a volume. So, okay. So this closed surface integral J dot ds, this gives a divergence of J V over a volume. You have integral. So this actually relates the closed surface to the volume. Similarly, you I think learned that in the mathematical course that the closed line is integrated to the area. That gives a Stokes theorem. Okay, so similar things that how they relate. Okay, one to one. So now we use this divergence theorem and we get this from these equations. Okay, so divergence of J dV over a volume is minus del del T C dV per volume, right? So that means that the same types of integral, volume integral, volume integral. So we can equate these two things. So then we can conclude that divergence of J is minus del del T, because C is independent of temperature. Okay, these are specific heat capacity. So C del del T. So we can write in more complete form. Del T, right? So now you know that what is J. So J is actually the heat flux. So minus kappa grad T, right? So then we put this. So we get del T del T. Okay, and divergence of J, that means grad to K. So it's kappa over C grad to T. So this kappa over C is called D, the diffusion constant, and grad to T. Okay, so we can write in more compact form. So this D grad to T, where D is kappa over C. So this is the temperature, how the temperature evolve with temperatures. Okay, so this del T, how the temperature evolve with temperatures is related to the grad to T. Okay, and the coefficient is T. Okay, so this is called the thermal diffusion equation. Thermal diffusion equations. Okay, and D is called the thermal diffusivity. Okay, so so here you have written this. Here is the thermal diffusivity. Okay, so this is the thermal diffusivity and this is the thermal diffusion equations. So similarly, just put in 1D. So this is calculated in 3D. So in one dimension, we get del T, del T, D, del to T, delta H2. Okay, this is in the one dimension. So this is how the temperature. So now this equation tells that this question that we previously asked, that how heat appears diffused from one place to another, right? So this is replace the delta H, T to delta H2, the space derivatives, and this is with time. So they are related. So now if we consider in steady state, okay. So in steady state, so can you tell me what is the means that the steady state? Hello. What is meant by steady state? Yeah, so that means the state of a system is time independent, right? So over a long time, the system state cannot change. Okay, so system cannot change. So okay, so then this implies that the delta t equals to 0. There is a no time variations. Okay, so over a long time, the temperature cannot change. So we define a system over a particular temperature, particular pressure, particular volume for ideal systems. Okay. So if we consider the steady state, that means the temperature does not vary with temperatures over a long time. Sorry, does not vary with time. Temperature does not vary with time over a long period. Okay. So that means the system is steady state. So when the system reaches the steady state, okay. So this thing must be whole. So which implies that grad to T equals to 0. So what is this equation? So the thermal diffusion equation reduced to grad 2 equals to 0. So this is called the Laplace equations. Laplace equations. So similar thing you observe in the electrostatics case. So when this static case you observe, that means this grad 2 phi is 0 in electrostatics case if there is a no source. In electrostatics case, there is a no current, electrostatic. Okay, so it is static means that there is a no variation in temperatures. So this grad 2 phi equals to 0 for electrostatics case. Okay, with no source, no source term there. Same thing here. Okay, so grad 2 T and grad 2 phi. So here is a phi is the potential, here is the temperature, is a field type something. Okay, so one kind of potential. It's not a potential, but the temperature is a field. Here is the phi. The similarity of these two equations. So temperature vary one point to another. Similarly, the potential vary one point to another. Okay. So if we solve that, we get a similar kind of things that we get in the electrostatics case. Okay. So you can connect this two things, similarity between these two equations. Okay. So similarly, suppose so similar case here we can include the no source term, and in this case we also include there is a no source. Okay, so then not consider any external heat source. Okay, that's why we compare with these two equations. So if suppose the source term is present, then how can this modify equations? Okay, so if the source term is present, okay, so I'm not going to this, so I'm just writing the uh, final equations. So if you are interested, you go through this book. Okay, I think I already referred the books. Is the Thermal Physics by Blundell. Okay, so go through this book, and I think there is some derivations. Okay, so you have to look into it. So if the heat generated at a rate is, if a heat is generated at a rate h per unit volume per unit time. So this is the rate. Okay, so this means that the heat is there is a heat pump. Okay, so they generate the heat at a rate h per unit volume and per unit time. Then the equations, the thermal diffusion equations becomes modified, and then the thermal diffusion equations, then the thermal diffusion equation becomes modified, becomes this del T over del T equals to d that to T plus h by c. Okay. So there is a source term explicitly present in the equations. So previously there is a no source term, and in this case the source term explicitly present. Okay, so that is for the temperature case. Okay, so similarly if we go through the particle case, the particle flux in 3D and this phi actually, so we give similar kind of equations. This is called the diffusion equations. So we go through this. Okay, so let's say okay, so let's go through this our particle case. So we are dealing with the temperature case, and now we're going to the particle case, and then gives the Brownian motions. Okay, so okay, so any questions up to this point? At any point we have not clear. Okay, so similarly if we go into the particle case. Okay, so okay, yeah, so suppose there are suspended particles irregularly dispersed in a liquid. Okay, suppose there be a suspended particles, suppose there be there be suspended particles irregularly dispersed in a liquid, dispersed in a liquid, right? So we have further two assumptions. Okay, we have to make further two assumptions that so two assumptions. So that first is that the each particle movement is independent of the other particle movement. Okay. So each particle movement is independent of the other particle movement. Each independent of the other particle movement. Second assumption is that so one particle movement in a different interval of time must be considered as a mutual independent process. Okay, so what is the interval of time? Okay, I will tell this thing. So first one particle movement in a different interval of time, in a different interval of time, let's say tau, this must be considered as a mutual independent process, must be considered as a mutual independent process. Right? So suppose you consider, let's say the time interval tau is 30 seconds. Okay? So in first 30 seconds the particle movement and the next 30 seconds the particle movement is a independent. Okay, that is good. So this interval of time it's not too small, not too large. Okay. So we have introduced a time interval. Introduce a time interval tau. Okay. Small compared to the observed interval of time. So small compared to the observed interval of time. Observed interval of time and large such that the motions and large such that the motion executed by two interval time, okay, are considered as a mutually independent. Right? Otherwise, they are somehow related, but that's why we are not considering too small, such that the is large is somehow that such that the yeah. So what do you call that? Yes. So okay, just a minute. Not too small and consider it as a large such that the motion executed particle such that the motion executed by particles executed by particle in two consecutive intervals particle in two consecutive interval, right, interval tau are mutually independent. Okay, so this is the moderate value, so we are not small or not large. Okay, so if you consider a very small thing, then this mutual independent things we are not considering, so they must fail. And if we not large, because then the we are not predict, because they are the observed interval of times. Okay, so the small compared to the observed interval time and large such that we are taking this thing at two consecutive intervals are mutually independent. Okay, so let's calculate that. Suppose there is a in suspended particles, so consider in particle, suspended particle. So consider in suspended particle, okay, and each interval tau. Okay, so each time interval tau time interval. So each tau time interval, let's say the x coordinate increased by delta, right? So x coordinate of particle increased by the amount delta, right? So that means delta. So this delta can be positive or negative. In directions they can move in one dimension. Okay. So then to think that delta must be follow some kind of probability distributions. Okay. So because each time intervals are independent, so in the first time interval tau, the x coordinate of a particle delta, and the next time interval tau, they can changes, right? So they must follow some kind of probability distributions. Okay, so delta must follow certain probability distribution. Certain probability distributions, since we are considering that each time intervals are mutually independent. Okay, so this value might be changes, so it depends on this value we get a probability distribution. Okay. And the distribution tells that how they distributed within over the whole range, okay, whole time intervals. So so again we consider, let's say, the dn particle. So dn so let dn be the number of particle, be the so dn be the number of particle, okay, which experience a displacement, which experienced a displacement delta, displacement between delta and delta plus, it's a d delta, a small range. Okay. So first time interval the x coordinate increased by delta, second something some extra, okay, delta plus. So you are considering the delta to delta plus d delta. Okay, so there are dn number of particles are increased by this time interval is in this range, delta to delta plus d delta. Okay. Okay, so this point is clear. I think this point is you must understand. Otherwise, we can discuss again. Okay. Yeah. Okay. So let's say consider we have time interval tau equals to 30 seconds, right? So first 30 seconds, the x coordinate of the particle, let's say, increase by delta, right? Similarly, if we change, let's say, delta for another 30 seconds, then they are mutually independent, right? So the two time interval, consecutive time intervals, are mutually independent. So first 30 seconds, the particle, the x coordinate increase by delta. The next 30 seconds, they not increase by delta. Okay, so they can be changed, right? So how do I know that which particles are which range? Okay, so that's why I'm ranging the delta to delta plus d delta. Within this range, how many particles are increased within this range? Okay, so we'll tell in the different way. So let's say we consider one particle, and this particle, the first time interval, the x coordinate of the particle increased by delta, and another particles, because the mutual the independent of all the particles. Okay, so that's why they can change delta plus epsilon, some amount extra or some amount less. So we consider this range, this delta to delta plus d delta. Okay, within this range, how many particles actually increased the x to this range? So delta must follow the certain probability distribution, means that we get a probability distribution phi in terms of delta. So different values of delta, we know the how many particles are there, right? So this actually gives the distributions of the particles. Yeah. Okay. So then so this in time interval tau, right? So this dn is the number of particles which experience a displacement between delta to delta plus d delta, and in the time interval tau, because time interval is same, right? But the two consecutive time interval can be mutually independent, right? So in this time interval, if the particle the x coordinate of the particle is increased by delta, next time interval it cannot be delta, it changes, right? It's a variables. So then we can write, so if the fractions of particle dn by n, okay, it gives a probability distributions phi delta d delta. So this is the probability. Okay. So then just normalizing that this is a probability distribution. Now you have integrate this minus infinity to the infinity about the whole range of delta. Okay, phi delta to d delta, because delta can take any value, negative, positive, any directions they can go. They can increase. Okay, so it gives a one. Right, this is the normalization. Right. Just think that the total particle in and they distributed in various uh, the functions of delta, that how they increased, and we can that is the fractions of the particle by n, we define a probability, and then we can the normalizing, that means the total particle is n, and that it gives a one. Okay. Yeah. So that means the phi delta. So if we explicitly written that phi delta actually tells that the probability of jump of magnitude delta of the particle. That means the increase the distance. Okay. So jump means the increase the distance. Okay. The jump of magnitude delta for the particle. Right. So this is the probability. And delta is the variable, so they can take any jump. Okay, so that's why the delta is a continuous variable. So okay, good. Then yeah. So then we so now we change the time interval tau. Right. So now we include the time. Okay. So how to include the time? So let's say okay. So let me check that. Yeah. So now we evolve the same kind of distributions in time. So, but in this case, we are considering that time interval tau is fixed. So each time intervals how the particle distributed. Right now, in terms of the distance, okay, they jump in terms of jump distance delta. So now we evolve this system with time. That means now we calculate. Now we calculate the distribution of particle. The distribution of particles at time t plus tau. Okay, from a distributions at time t. From a distribution at time. Okay, so we are calculating the distributions of particle at time t plus tau from a distributions at time t. So we know the distributions at time t. So this is the case at a particular time. Okay, and time is actually the time interval. Okay, so now this time interval actually changes. So you connect this thing, why we or what kind of extensions we have to do. So there is a no time. Okay. So at a particular interval of time, so this time interval is fixed. Now we are varying the jumping distance, okay, how the particle jump at this interval of time, and depend on this jumping distance we are calculating the fractions of particles, number of particles, and they distributed in this way, right? So now we allow the time, this time interval actually changes. Okay, so just a minute. Okay, this clear up to this point? Okay, so then our probability distribution functions not only this delta, but it also comes in the time. Okay, so then is the, then let f of xt is the number of particle per unit volume. So try to connect with this. Okay, so here I am saying that what, just a minute. Particle, yeah, so f of xt is the number of particle per unit volume. So here we not consider any unit time. Okay, okay. So in this case we are considering that the dn is the number of particle which experience a displacement between the delta to delta plus d delta in a time interval tau, right? So it's a specific thing, so in a specific time interval, right? And this dn by n actually gives a probability phi delta. So but in this case we are not considering any time interval, just considering a unit volume. Okay, and this is actually f of x. Okay, so it depends on time. So then we can write that f of x t plus tau minus infinity to infinity f of x plus delta t pi delta t delta. Yeah. So that means what do we do here? Okay, so let's discuss this thing. So let's consider the two thing. Okay, so on the x-axis there are 2 points. One is that x, another is, let's say, x plus delta, right? So at distributions at time t and the space x plus delta evolves to a distributions at time t plus delta t at space x. Okay, so I think there is. So what is this mean? What is means this by this equation? So let's. So that means the distributions, this f of x t plus tau is the distributions at x at time t plus tau, and we know the distributions at t and x plus delta, and they evolve in the same case as we do previously. Okay, so when we integrate over minus infinity to infinity phi delta d delta, it gives a 1, So that means this, in this case the delta is a variable. In this case the right hand side, okay, so left hand side there is a no delta, right, and the right hand side there is a delta. Okay, and there is a delta variables, and over this whole delta range, that means they can any jump at a particular time interval. Okay, and we have integrate, we get a 1. This one is not clear, right? Yeah, okay. Okay, so suppose we know the distributions at a time and a space x plus delta, right? So at this point, at a particular time t, and we know this point x plus delta, this at a particular time t, the distribution is f of x plus delta t. So now these distributions evolve at, let's say, t plus tau time, okay, at x. So this is time after tau times, okay. So now the time is t plus tau, okay. So these distributions evolve at a f of x t plus tau, right, right. So if we know at x plus delta at a time t, and then we evolve this after time tau, this, okay. So how to write these two things, okay. So then we go back to the previous case, okay. What we do in the previous case. So in the previous case, at particular time interval, okay, so with the number of particles which experience the displacement between delta and delta plus t delta in a particular time interval tau, okay. So then dn by n is phi delta t phi. Yeah, so that means okay, so this picture is clear, right? So now we consider, so what is the integral. So think that, so okay, so okay, so go on to one, okay. So first that if x t plus tau, and we know if x plus delta tau, we're going from this point to this point, okay. So here delta is a independent, delta is a variable, okay. So we integrate over delta x into all possible jump from x plus delta to x, right. So we jumping that x plus delta to x, right, and delta can be take any value, okay. I do not know what is my x plus delta, right. So that means if we integrate over delta, and that includes that we can consider any point. So x point is my fixed, but x plus delta t, this point is not fixed. They can take any value because the delta can take any value, right. Yeah. So but we reach this point at particular time tau, right. So that means, so what, wow, so then the delta variation, what is the probability distribution for this delta variation? I mean that, yeah, yeah, tell. Yeah, phi of delta. Previous case we are defining the phi of delta, right? So for the jump case, right? So then we multiply this phi of delta times d delta over the whole delta range. So that includes that we can take any values of delta, okay, with a probability phi delta, right? Because delta follow a certain probability. So if we take a delta, then the corresponding there is a probability that is called the phi delta. So we have to multiply it, okay, because you have not choose a randomly. Delta is a follow some probability distributions. Okay, this is the phi delta. So that's the equations actually takes. Okay, so now it's clear, right? Yeah. Okay, so then we erase these things. So now we have to solve this equation. Okay, so this is a integral equations. Once you see that the how this point and they are connected by integral equations. Okay, so this kind of equation called the integral equation. Integral equations. Now we convert this equations to a differential equations. Okay, so this is a integral equations. Now we convert these equations to a differential equation. Differential equations. Okay, so we convert this thing. So what is the corresponding differential equations? So what is the corresponding differential equations? Then so we consider, let's say tau is small. It's not too small, but it's a moderate small. So tau is, let's say, so small. Okay. Then if we expand this f of x and t plus tau. Okay. So if we expand the Taylor series, okay. So this x t plus tau delta f delta t. So in this case, we are considering the only t plus delta t, and if x you are taking as a constant. Okay, because we are only focusing that t. Or if you know that the how to the two variable functions expand in a Taylor expansions. Okay, expanding in a Taylor expansions. Okay. So so this way that if we vary the tau, and then we can f of xt and del tau del f of xt by del t, and we are neglecting the higher order term. So higher order term we have neglected. Okay. We have neglect this higher order term. Okay, and similarly again we're taking that the delta is a small. So we consider that the, yeah, okay, so here is the assumptions that why we choose delta is small, because delta it can take any value, right? So suppose we consider the delta is small, then what we get that if x plus delta t is f of xt. I will come to this point why we take this delta is small. Okay, so f of xt plus then delta f of xt delta x plus delta square by 2 factorial delta to f delta x2 plus dot dot dot. Okay, now putting these equations into this. Okay, putting these equations into this. That's the one. So if we put that, what we get that f of xt plus tau del f del t equals to minus infinity to infinity f of xt times phi delta d delta plus this thing. So delta phi delta times d delta times delta f over delta x plus delta 2f delta x2 delta square by 2 factorial I delta d delta, right? Okay, this one is clear. Hello. Okay, so in this case we choose a delta small. Okay, so that is one approximation that why we choose the delta is small. So in the previous case we have not assumed that delta is a small. Delta can take any value. Okay, that's why you use minus infinity to infinity. But now if we consider this delta is a small, so impose a constant that my delta is small. That's why we are considering up to second order delta square. So the tau is very small. That's why we are only considering the first order. In the delta case, we are considering up to second order. So it's not too small, but it's a moderate. So if we consider this thing, what we get? So then we can write this thing. Okay, and what is this value? Minus infinity to infinity f delta d delta. It gives a 1, right? Normalizations of this. Okay. So then we put this thing. So fxt is cancelled. Then tau delta f delta t is. So these thing and this thing actually cancel. So this goes to f of xt and this f of xt, this f of xt cancel, and then tau del f del t equals to what is this value? So this value actually 0. How to know? So okay, so I come to this one. First I write this thing minus infinity delta 2f delta h2 del square by 2 factorial I delta d delta, right? And this delta I delta d delta, it gives a 0. Why? It's 0 because we're considering that the phi is a even function. Okay, right? Because I'm saying that in the previous case that the phi is there is no preferred directions, so they can move positive directions or negative directions, right? So phi delta is phi minus delta. This is in understood some. This one, no, this is not a assumptions. Okay, so what is means that? So we are calculating it at which jump delta, how many number of particles are there, right? That is the distribution phi delta, right? But each jump can be positive or negative. In any directions they can jump, right? So that means the probability, but the particle number the same, right? Particle number is uh, based on the jump, right? And not is the particular directions we have to calculate, right? So they can move in the positive x directions, this delta jump. They can move in the negative x directions, this delta jump, right? So that's why we have these things that we can go positive or negative. The number of particles within this jump is same, right? So there will be no preferential direction. This means that delta has no preferential directions. Okay. So the magnitude, the jump of magnitude, jump of magnitude delta has no differential direction. So remember, we are considering only one decay, right? Directions, right? So one decay. So this distribution was just. So if we this thing and then why this integral then 0? We consider phi delta equals to phi minus delta. So why this integral 0 understood, right? Because this is a even function and delta is a odd function, right? So when you integrate full range, even function and odd functions, so we get a equal and opposite sign. So when we add these things, we get a 0. Okay. So then we get these types of equations. Okay. So now, so what is this equation? This equation is actually that del f del t it d del 2f delta x2. This is not any delta dependence, this quantity. So we can take outside. Okay. We can take outside of this integral. So what is that? D is actually the rest of this quantity 1 over tau integral minus infinity delta square by 2 factorial phi delta d delta. So this is your d. Right. So if we consider that delta is a small, that means the particle jump is some values, not considered too large jump. Okay. But still the whole the assumptions is valid because we are only neglecting delta cube, delta I to the power term, delta 4, and then we can get this kind of diffusion equations. So this is a diffusion equation. Okay. And D actually gives a diffusion coefficient. Right? Good. So, okay, so remember that the function actually x and time, right? It's both space and time. Okay. So then you understand that this is the differential form of this integral equations. Okay. So this is your integral equations. And I say I am asking what is the differential equations of this integral equations. The integral equations is exact. There is a no impose on this delta. But when we go to the differential form, okay, so we make an assumption that delta is a small, okay, and we get this kind of diffusion equations. Okay. Diffusion equation is the differential form of this. Okay. So now how to solve this equation? So let's go into the quickly the solutions. Okay. So how to solve this equations? Okay. So are you done the previous any mathematical course that how to solve this differential equations of this kind, both space and time derivatives involved? Okay. So I think this might be helpful. Okay. So then let's solve this diffusion equations. Okay. So let's consider at t equals to 0, at t equals to 0 all the particles concentrated at x equals to 0. So at t equals to 0 all the n particles, we are considering n particles, right? So n particles are concentrated concentrated, okay, concentrated at x equals to 0. Okay, so that means the particle at the later times the particle try to diffuse. Okay, so first consider the particle concentrated at x equals to 0, and then when the time evolves the particle going to diffuse. Okay, so then how to write this mathematically? Okay, so mathematically there is a called the delta functions. Okay, so mathematically if we write that if x 0, okay, is actually the total number of particle in delta x minus 0. So delta functions actually tells that this kind of things that mathematically we replace the at only non-zero value at x equals to 0 then, and x not equals to 0 that gives 0. So what is the delta x minus 0 is only 0, it's equals to 0 at x not equals to 0, and delta x minus 0 it equals to infinity at x equals to 0, right? So how to know that then in, so this is actually the normalizing. So when we in this the f of x0 over a whole range dx, and this in delta x minus 0 over a whole range dx, right? So again this is the 1. Okay, so this gives you in, okay, so I will discuss this point. Okay, so this gives you in, right? So it's clear. So considering a mathematical functions that is called the delta functions. Okay, so this is actually delta functions. Delta functions. They can writing this as suppose if in particle concentrated at x equals to 0, and when the x not equals to 0 that means they gives 0. So how to write this types of statement into mathematical expressions? Okay, so then delta function can help you. Okay, so delta function is types of mathematical functions. Okay, so they define in this form that delta x minus 0 equals to 0 when x not equals to 0, that means there is no value, but at x equals to 0 they gives infinite, but they normalizing in this way. Okay, so what they normalizing is that minus infinity to infinity delta x dx it gives a 1. So that means that delta x is infinite, but your this delta x, the strip, this integral time, so this actually your width. Okay, so this total value is 1, right? So this means that this kind of peak few observes, right? So if this delta x is tends to 0, this is goes to infinity, but if you multiply these two things we get a 1. This is the normalization. This is the normalization of the delta function. So okay, so this point is clear, and this gives that the total particle is n. So we integrate over the whole range dx, it gives n. This gives the total particle, and that's why we said here n. Okay, it's a backtrack calculation. So then also there are some also if we write that f of x0, yeah, so also you write f of x0 is minus infinity to infinity f of x delta x minus x0 dx. So this is a property. So we integrate over x, the x0 is at f of x. This is the property of the delta functions. Okay, so you learn in the mathematical physics courses when we go through this. So we use this two things. One is the delta function concept, and another is this function. And another thing is that the Fourier transform of this. Okay, so f of xt This is your position space wave functions. Okay. So you are going to this xt space to kt space. There is some abstract space is called the kt. So let's say we are defined this way, that minus 2 pi minus infinity to infinity e to the power I kx f tilde kt. Okay. So we define another k variable, right? And integrate over k, we get a x. Okay. Yeah, so complex integral, but so depending on that, what is the function? So f tilde kt. So e to the power ikx is a complex, but yeah, so we have to do the complex integral, but depends on if the function is analytical, we can solve analytical. So okay, so you have remember that what is that f kt, f tilde kt is, there is a more abstract space and there is a, so this is we need, and we have to relate this f of xt to f of kt through e to the power ikx. Okay, so this ikx actually a kind of a complex map. Okay, you can think. Okay. Yeah, so this is a definition that we are going to from one space to another space in this way. Okay, if this space are, there are certain another conditions also there, but so when we go through the Fourier transform, okay, in your mathematical physics course, we will then there it will be discussed more elaborately. Okay, so it's a Fourier transform. Okay, so then if we write this diffusion equation in terms of f tilde kt. Okay, so this diffusion equation, now what is the diffusion equations? So your diffusion equation del 2 f delta x to d del f delta t, this, right? So now we write this equation in terms of f tilde. Okay, so if we write it in terms of n tilde, then so let's first we write this del f del t. Okay, so put this f in this way. So this implies that del t 1 over 2 pi minus infinity to infinity e to the power I kx f tilde kt dk. So this del t, because any variable a t k x, they are not depend on time, so this del tilde actually operate on this f tilde. Okay. Del t operate on this f tilde. Okay, so this actually gives that 1 over 2 pi minus infinity to infinity without affecting any other variables e to the power I kx del f tilde over del t. That this f tilde is only depends on time. Okay. Right. So the derivatives comes to the into the integrations inside the integrations. Okay. And similarly for the right hand side, del 2f del x2. Okay. So in this case again there is a no x derivative here, so k derivative we put this form, but so okay, so when we write this del 2f delta x2, this gives actually minus k square infinity, yeah, 1 over 2 pi there. So 1 over 2 pi, and when you operate this thing e to the power ikx, so there are two ik comes. Okay, so ik is ik square, I square k square, and I square gives you minus 1. Okay, let's write the explicit. So it's ik times ik e to the power ikx f tilde kt, because this x they operate on this e to the power ikx only, so f tilde kt and dk. there is a 1 over 2 pi factor. So it gives that 1 over 2 pi minus infinity to infinity minus k square d f tilde So now we just put into this form. Okay, so these equations actually gives just two line derivations, because this e to the power minus ikx tk e to the power minus ikx tk both side there. So we are just only gives this kind of equations, that delta f tilde delta t, it gives you that minus k square f tilde. Okay, it's clear. Other thing is just comparing these two equations. Okay. Hello. Okay, so it means that we are reducing this second order differential equation into a first order differential equation, right? Okay, so there is a d factor there. I miss, because there is a d factor. So there is a d factor. So that means it's a first order equations. First order equation in Fourier space. In Fourier space. Okay, because f tilde is a Fourier transform of fx. So once you solve the equation and then go back to a xt space. Okay. So that is a trick that we calculate. We have to solve the second order differential equation. We go to the Fourier space, and there is a first order differential equation, and can easily solve, and then again go back to the position space. Okay, x space. So then what is the solution? This f tilde kt is just f tilde k0 times e to the power minus k square kt. So this is the solution. So just f tilde we are divided and delta outside, and we can choose t equals to 0. So at t equals to 0, okay, so the function is f tilde k0. So initially we choose at t equals to 0 f of x0. So f of x0, and that Fourier counterpart is f tilde k0. Okay. Similarly, the definitions of this, that f tilde k0, f tilde k0, f tilde x0 related. Okay, so in this way they are related. Okay, so then so once you solve this, so now we go into the x space again. So then we put that f of x0 is 1 over 2 pi minus infinity to infinity e to the power ikx f tilde k0 dk, right? So if you solve these equations, we get a f tilde kt. Okay, so let me check. Yeah, f of x0 dx is n, and yeah, so this equation tells that how f of x0 and f tilde k0 related. Okay, so this is the same way as we define here. Okay. So f of xt and f tilde kt, how they are related. So then we again, so once we solve this equation, we go back to that. So this is, let's say, time at t equals to 0 and t at particular time t. So we know f of kt, we know f of xt. So this is a trick. We go to the Fourier space and solve, and they again come back to that. Okay. So once you know this exponential part of things, we come back to this part. Okay. So once you solve this, okay. So this is two. Okay. So I'm first. Okay. So what is f tilde k0? So f tilde k0 is actually gives a n. So this minus infinity to infinity f of x0 dx is actually n, right? So here we define that f of x0 minus infinity to infinity f of x0 dx, it gives a n, right? So similar way, so this actually this is equals to minus infinity to infinity f delta k0 dk. This also gives you a n, right? Just a minute. No, I think we have to write down the explicit form. So when we write this f of x0, okay, so let's write this f of x0 in delta x, okay, and so we can write this f of x0, yeah. So then we just write that so in this equation, f of x each 1 over 2 pi minus infinity to infinity to the power ikx f delta kg dk. So now put this right hand side in delta x 1 over 2 pi minus infinity to infinity minus infinity to infinity ikx f delta k0 dk. Then and we use the identity delta functions. We use the identity that delta x, so I written that 1 over 2 pi minus infinity to infinity e to the power ikx dx. So once you know this, ikx dk, so once you know this identity, we can put this form in over 2 pi minus infinity to infinity e to the power ikx dk is 1 over 2 pi minus infinity to the power ikx f delta k naught dk. So we compare to both sides, we get that f delta k0 is actually n, right? So this is a delta function identity. We have to do one more step from this equation, so we get this. I think this equations. So you have to do one more step, we get this kind of identity. Okay. Or if not, then I can discuss in the next class. Okay. So we have get this in, right? So then your f delta kt. So once you know if this, once you know this, okay. So once you know this f delta kt, so then you can just write that f delta kt is in e to the power minus k square dt, k square dt. So now we can solve the Fourier transform equations. Okay, so f of xt is just the Fourier transform of this 1 over 2 pi minus infinity to infinity e to the power I kx e to the power, so n e to the power minus k square dt dk, right? So then once you solve this equation, this is one kind of complex equations. Okay, so we will solve in the next class. Okay, I am so today I am just taking the answer. Okay, so if you not solve you, then I can do in the next class. Okay, so this is solved by complex integrations, solved by complex integral. Okay, so it gives actually in our 4 pi dt e to the power minus x square by 4 dt. Yes. So once you know this thing, okay, f of xt, we know, right? So this are the integration solving you have to try, then if not done, then I can do in the next class. Okay, so this point is clear, right? So this is the distributions of this bounded of this diffusion equations. Okay, so now from these distributions, if you calculate x average, what is the x average? Okay, so what is the normalizing? So if we just try to calculate normalizing f of xt dx, it's normalizing is in, right? As you already told here. So normalizing it cannot change. So f of x at t equals to 0, it gives it at t equal at t it the number of particle is fixed, right? So minus infinity to f of x0 dx is in. At any time you have to do the same thing. It gives a n. Okay, number of particle is not fixed, but they are diffuse. Okay, so they are distributions of a spread. Okay, so let's say what is the x average? So how to calculate? We put that in the minus infinity to infinity x f of xt dx over normalizing minus infinity to infinity f of xt dx. That is the definition of the average. But this gives you in, and there is f of xt, there is a in. So actually it gives that minus infinity to infinity 1 over root of 4 pi dt x e to the power minus x square over 4 dt dx. So the integration range is minus infinity to infinity, and you are integrating over a dx. Can you tell me quickly that what is the answer? So then again same trick. This is even function because e to the power minus x square, right? So this is a even function. This is your odd function. We are integrating over minus infinity to infinity. So both sides. So once it changes sign, another is not. So you get a 0. Okay. Similarly, if you calculate x square average, okay. So I am not going into this. Okay, just calculate the same way. So you have calculated 1 over a normalizing factor minus infinity to infinity x square f of xt dx. Okay, so you get the 2 dt. Okay, so you get 2 dt. That means the x square average you get 2 dt. Okay, so similarly, if you consider a three-dimensional motions, okay, let's say x, y, and z, and all the directions of motions are independent. So you calculate r square average 2 dt plus 2 dt. So this is actually x square average plus y square average plus z square average because they are all independent, and then both are 2 dt, so it's 6 dt. So in 3 dimensions we get a r square average 6 dt. But experimentally determinations that this quantity, right? Experimentally determinations which is a mod of root of x square that average. That means the root 2 dt. So this is the experimentally observed from the determinations for Brownian particle. Okay, so we will derive in a different way. Determinations of Brownian Brownian. Okay, so I think we will stop here and discuss some assignment problems. Okay, and then we'll stop. Okay, so and the Langevin equation. So how they modified the Langevin formalisms. Okay, so it gives the exactly the same answer. Okay, so we'll discuss in the next class. So then the interesting that what is exactly this 2dt comes from. So the Langevin formalism is we'll discuss in the next class. Okay, so that's also interesting that things. Okay, so now let's plot this thing. Okay, so what is mean that suppose if you plot this functions f of xt. So initially and we plotting with respect to x. right? So initially the functions at t equals to 0, there is some kind of delta functions. So particles are localizing at a particular small range at let's say at x equals to 0. So we have to choose this is your point x equals to 0. This is your origin. So this is your origin we choose, and so at t equals to 0, the particle distributions looks like it. So when we increase the time, the particle is evolved around the x equals to 0. There is a Gaussian like this type. So that means particle try to diffuse. Okay. So this initially depth is too small. Now it is depth is too large. What is that? The height. So height is decreased. Okay, and depth is increased. So that the total product is constant. So initially we see that the integrate of our whole curve we get a 1, right? Minus infinity to infinity, minus infinity to infinity f of x0 dx, it gives n, right? So if we increase at time t f of xt dx, it also gives n. So that means if we increase the time, the probability distribution spread out, okay, because they are diffuse, so it's just spread out. And if you just plot this function in your any graphic software or online, okay, if you plot this function, okay, so once you plot these functions, okay, you get that this kind of distributions, okay. So this kind of distribution, so this kind of distributions. So that means that they increase the speed and decrease this height, but the total probability is constant. So this thing is constant. Okay. 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 So now quickly going to the questions. Okay. So okay, solve the assignment 4 problems. I think assignment 4 problems is informative things that I think you know that what is the Brownian motions, and for which case the Brownian motions is increased. Okay, the motions of the particle is increased. Yeah, so that we discuss, and there is some experimental constants. Okay, so let's set the space side constant. So okay, so what is the barometric equation? I mean, the phasors at a particular height and depends on this particular height. So it gives the barometric equations. Okay. So barometric equation tells that the pressure P at a particular height Z is related to P0 into e to the power minus m g z minus z0 over RT. So here m is the molar mass, that is the total mass, and z0. So at z equals to z0, at z equals to z0, pressure P equals to P0. That means P of z0 is P0. Right. So this is P0 at z equals to z0, and at z this formula. Okay, and third derived in this formula in third derived this formula in the class. So we use this formula. Let's consider at temperature T1. Okay, and at temperature T1. Okay, so the pressure P. Okay, so temperature T1 and distance Z0, the pressure P0. It's a some value 101,325 Newton per meter square. Right? So we calculate at jet distance, pressure P1 is reduced by P0 by let's say 4. Okay. So then at what distance we calculate? So then how to calculate? I put this formula that P0 by 4, P0 e to the power minus mg z minus z0 by r. That's a particular temperature T1. So we do not know z0, we do not know z. So we written z and z0. How do we know p0, p1? So they just cancel. So that means e to the power minus m g z minus z0 by r t1, it gives 1 by 4. Right? 1 by 4. Now, how to calculate z? Yeah, so they again the functions of, so if you know t1, if you know z naught, if you calculate z, right? Okay. So then this problem can be solved. Okay, so now the next thing again the same thing. Let's say the at a height z is 1 by 8 times the pressure at the base, the ratio of the density. Okay, so once you know that this formula P actually n kVt, right? So the pressure and the distribution is the same kind. Okay, so pressure and the number density follow the same kind of distributions at a particular temperature. If the temperature T is fixed, okay, at a particular temperature, the pressure and the number density follow the same distribution, right? N equals to n0 minus mg z minus z0 by r. So the pressure and the number density follow the same distributions. Okay. So the similar way we calculate then how the number density can change. Okay. 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 So then this thing also can be done, and okay, so one more problem. Let's say, okay, so let's go into the 6 number problems. So let's say a gas or molecule weight m is kept at in a column of height h and the temperature T. So the pressure and the number density at the base G0, Z0, P0, N0, at what height the number density falls 1 by E. Okay, so number density m means 1 by E means the N0, let's say inverse. Right. So once you know this thing, number density falls 1 by E of the initial value. Okay, so then we just put this thing. So then means let's put this formula. So in z minus z0 by rt equals to minus 1. Right? So then we can calculate z. I think you know that one is z. Okay. So then the third problems, sorry, seventh problems. So we know that how to calculate the x square average, right? So once you know the x square average, let's say there are success. Okay, so each 30 second time interval, 30-second time intervals, there is a specific delta is there, right? So delta equals to some value there. So 30-second time interval, let's say the values of delta is given 5 set of values. So 0 to okay, 3 and 4, 0.9, this kind of values are there. So if you calculate the delta square average, so how to calculate the delta square average? So once you calculate this delta square average, okay, so delta square average, that means so you just put that how much number of particles in sum over delta square, right? So delta I square is the n is the total number. So remember that the x average 0. Okay, so I think they are in this case if we choose, let's say 3, but 2, but 5. So in such a way that the delta average is 0. Okay. Yeah, let's say minus 3 and in this setup. So delta average is 0 and 0 is not. So you calculate this delta square average. So in this, using this formula you calculate. Okay. And then once you calculate, and then how to diffusion coefficient. So this delta square average is related to 2 dt. Just calculate this thing. And if you know this t actually 30-second time interval, t is 30 seconds. Okay. And you calculate delta square average here. So then 30 is delta square average. So you know delta square average from this, and you calculate t. And you know the t, and you calculate t. Right. And then the other two problems are the informative problems. So you answer these questions. And the last problem is, so in an experiment of Brownian process, the RMS displacement of the horizontal directions of a minute spherical particle suspended in a water to be found this, and over a 30-second interval at a 27 degrees centigrade, at which the viscosity of water is this. If the universal gas constant is this, the number is this, calculate the radius particle in a micron. Yeah. So then we have used this formula that D, the diffusion coefficient is actually the kBt of 6 pi eta r. So if you use this, and then we can replace this delta d, it's delta square average by 2t equals to kBt replaced by RT by Na, Avogadro number, and then 1 over 6 pi eta r. So you know delta square average. I think there is a given. This is the RMS displacement. It's what is the RMS? The delta RMS, right? Which is root over of delta square average, because delta average is 0. Okay. So since that since delta average is 0, so delta RMS is root over of delta square average. So you know that the delta average square, and you know the time interval d. Okay, and you know the Avogadro number Na, and everything is known. We calculate just r. Okay. So the r is yeah. So r is r t t by 6 by eta Na delta square. Hey, this is the radius of this particle. Okay. Yeah. Any questions? Yeah. So I think that there are no many. There are no other questions you have to solve. Assignment problem is already solved. So also know the formula. We just put in the formula and we get that. So there is no difficult task. Okay, so then I think. Okay, so then I think I will stop here and we start from tomorrow. And okay, so today I am not discussing this Langevin formalizations. Okay, so we'll start. We will discuss tomorrow. Tomorrow in the next session. Okay, so we will see in the next session. Okay.